function notation, it would be f of x equal a times b to the x. And each part stands for something. So this a here is our initial amount that is given to us. And this b is the growth or decay factor. And this b is always positive. So if it's bigger than 1, it's our growth factor. If it's less than 1, it's a decay factor. And this base b can be also looked at as 1 plus or minus r, where r is the percent growth or decay. So we can rewrite the model, the function, as f of x equal a times 1 plus or minus r to the x. So when r is the percent growth, we're going to add the r. So, and when it's the percent decay, we're going to subtract r. We're going to look at different examples so that it all makes sense. Alright, so here's our first example. A colony of bacteria starts with 1,000 bacteria, and the bacteria are doubling every hour. Part A, write a model for the population P after T hours, and part B, how many bacteria are there after 7 hours. So I know that my growth factor is 2 because here it tells me that the bacteria are doubling each hour. So this part tells me that my growth factor is 2. And then I started with 1,000, so my initial number is 1,000. So this gives me my A, and this gives me my B in the general model. To come up with a model, you can think of it like this. So I started with 1,000 for part A. I started with 1,000. This is what I started with, and then after 1 hour, this 1,000 doubles. So 1,000 times 2, and then in the second hour, this number that I have here gets multiplied by 2 again. So 1,000 times 2 multiplies by 2 again. And then the third hour, 1,000 times 2 times 2 times 2. So as you can see, this is like 1,000 times 2 to the first power. This is 1,000 times 2 to the second power. And this is 1,000 times 2 to the third power. So if we follow this pattern, we're gonna get to this point that these 1,000s times 2 to a power of x, and this x represents the hour, the time. Or you can think of it as y equal a times b to the x, and our a was the initial amount, which is 1,000, and the b is the growth factor, growth or decay factor, which in this case we have growth factor because they're doubling, and this x is just a variable. So, and then you have to adjust the variables as the question asks. So the population after t hours is 1,000 times 2 to the t. So that's it for part A. Okay, so we found out that in part 8, our initial amount was 1,000, growth factor was 2, and then our model for this population is 1,000 times 2 to the t. And then part B is asking us that how many bacteria are there after t hours. So you can keep doubling the 2's until you get to the 7th hour, or you can just plug in the numbers. So after 7 hours, P of 7 is 1,000 times 2 to 7. And make sure to do the order of operations correctly. So first we do the parentheses. It's 1,000 times 2 to the 7 is 128, and then 128 times 1,000 gives me 128,000. So this is the population of bacteria after 7 hours. So this is it for part B. Alright, here we have another example. A A mouse population starts with 400 mice. During an experiment, only 1/4 of them remain each month. How many are there after 6 weeks? So we start with 400. So this is our initial amount. And then only 1/4 of them remain each week. So my initial amount, I'm going to write it here. Is 400. And the decay factor is 1/4. And I know that I have a decay factor because it's less than 1. Remember, whenever we said that whenever b is less than 1, in the formula y equals a times b to the x, whenever this b is less than 1, I have decay factor. So this 1/4 actually means that each month 1/4 of them remain and 3/4 of them die. But I just need the 1/4 in this question because this b here has whatever remains from the initial amount. So in this formula, in this model, I'm going to have 400 times 1/4 to the x, and then we have to adjust the variables. So the population after t months, because t is in month, is 1/4, is actually 400, the initial amount, times 1/4 to the t. And then I want to know how many mice I have after 6 weeks. So this 6 weeks, this t here is in months because the situation is given to me for each month. And this 6 is in weeks, so I have to convert the 6 weeks to months. Each month is 4 weeks. So 6 weeks is actually 1.5 months. So in my model, I'm going to have the population after 1.5 months. So it's 400 times 1/4 to 1.5. Okay, so if you plug this in your calculator, 1/4 to 1.5 and then times 400, you're going to get 50. So that means after 6 weeks or 1.5 months, you're going to have 50 mice. Alright, it's your turn now. Go ahead and pause the video, try to do this question. We'll go over it together then. Okay, a population of rabbits start with 500. Due to bad weather, each year 3/4 of them die. Come up with a model for the number of rabbits n after t years. So the initial amount is this 500 here. So my initial amount is 500. And then for my decay factor, I have this 3/4 here, but this is not exactly my decay factor. So notice that, I know that this is worded differently, but notice that how similar this question is to the last one that I just did. So 3/4 of them die, so that means 1/4 of them remain. The last question told me that 1/4 of them remain. So my decay factor here is 1 minus 3/4, which is 1/4. So it makes sense because if 3/4 of them die, so how much remains? 1/4 of them. So in this model, y equal a times b to the x, my initial amount is 500, and my decay factor is 1/4 to the x. And then to adjust the variables, we just have to write n of t, the number of rabbits after t years, is 500 times 1/4 to the t. So this is the model in terms of n and t for this question.